We'll be talking about ill-posedness of truncated series models of water waves. This is especially joint work with Jerry Bona and David Nichols. At the end, I'll mention future direction that includes joint work with Mike Siegel. We've published 2 papers on this. The main thing that I'll be talking about is in this first article listed, Ambrose, Bona, Nichols on ill-posedness of truncated series models of water waves, came out earlier this year in Proceedings of the Royal Society. And our earlier paper, which I'll talk about at the end, is by the same authors, well-posedness for a model of water waves with viscosity in DCDSB from 2012. Okay, so if we are talking about the initial value problem for water waves, then as everyone in this room surely knows, we're talking about the initial value problem for the incompressible Euler equations bounded above by a free surface, and we're taking the fluid to be irrotational. Okay. There's a long history of studying the well-posedness of that initial value problem. There were certainly early results. Other people have mentioned these, especially probably Siju Wu. Early results by, say, Nalimov and Yosuhara and Walter Craig. Those early results tended to be short-time, small data results. So they weren't really existence theorems for a wide class of initial data. You had a restriction that it was for very short time for very small data. So the first really robust existence theorem was Siju Wu's result, which I think she was saying 17 years ago, I guess 1997. So that's Wu's 2D paper in 97, and then she followed it with her 3D paper in 99. And then after she started the ball rolling with these general well-posedness theorems, a number of other proofs followed. So there are very many at this point. David Lon, Nader Masmoudi, and myself, Cordoba, Gancito, various others. And those are the short-time results. Then there are various results for all time also. Again, Wu's results, Germain Masmoudi Chata, Alizard and Delors, and Pusateri and Ionescu, and even others. Okay, so at this point, there's a lot of well-posedness theory for the irrotational water wave. It's understood fairly well. And people have done this many different ways. So everyone does something different, everyone does their own thing. Siju's big results came through complex analysis and Clifford analysis, using a Riemann mapping in the 2D case and Clifford analysis in 3D. So the Riemann mapping is a change of variables. You know, obviously you take your fluid domain and you map it to a simpler fixed domain. Okay. David Lon made a change of variables and used a Nash-Moser iteration. Nader and I used a Howlow and Grubb-Shelley type formulation, which I will be talking at great length about next week in the summer school. So this is a vortex sheet formulation of the water wave using special geometric independent and dependent variables. So Masmoudi and I used this Howlow and Grubb-Shelley type formulation, which includes a change of variables, and we made estimates that are uniform in surface tension. So more or less, everyone who does a well-posedness proof for water waves needs to estimate the growth of solutions, and somehow changing variables before you make the estimates is always helpful. So everyone has their own change of variables, but this seems to be common to all the approaches. Okay, so you set the variables to be very convenient, and then you can make your estimates. Okay, and so one thing I want to say about that is that changes of variables seem to be important for the different techniques, and more generally, I think it's fair to say the well-posedness theory was subtle. Okay, so it took a long time to develop, and there are various tricks involved. It's not a straightforward thing. Like, it's not, you know, the time derivative is in the same function space as the unknown, and you can do an ODE theorem, you know, or it's not a simple argument. You have to be very careful with it. Okay. Yes.
So I got a question about the history, actually.
Yes.
So it took a long time, and then it looks like in a relatively short succession, entirely different approaches came out.
That's right.
Was there something in the first one that got past the subtlety that was then used by the others, or?
So I can tell you about my work with Masmoudi is that there's only one aspect of Wu's work that we relied on, and that was her key lemma that grad p dot n has a fixed sign as long as the interface is non-self-intersecting. Other than that knowledge of a priori control of what you might call the Taylor condition or the Taylor quantity or whatever. Other than that, we didn't especially use her techniques. I'm not sure. I'm not sure if other people especially used insights that she made other than that also. Yeah. So
Time was right.
yeah, a lot of things happened at once. The biggest thing that she had was the lemma about the Taylor condition. Other than that, I'm not sure why. Yeah, most people don't use, for example, the Clifford analysis that she does in higher dimensions. Yeah, I don't know. Okay. But yeah, still certainly she got the ball rolling, and then yeah, other people added their own techniques. I mean, it's possible that it's possible that one effect is that her breakthrough attracted attention to the area, Okay, so moving on to the subject of the talk, the truncated series models. So one way to write the evolution equations is in what we're calling the Zakharov-Craig-Sulem formulation. Here, eta, so again, as I'm sure people in the audience know, eta is the elevation of the free surface, and xi is the velocity potential restricted to the free surface. And so you can write evolution equations for eta and xi. dt eta is y eta of xi minus dx eta, x eta of xi. dt xi is minus g eta, g is the gravity, plus some other terms. And I'm not going to dwell on what all these terms are. The important thing is that the capital X and the capital Y are operators related to the Dirichlet-de-Neumann operator. And the Dirichlet-de-Neumann operator is for the specific fluid domain. The fluid domain is changing over time. It's described by eta. So these operators depend on eta. Okay. So this is a standard formulation in the business. Okay. So the truncated series models then, as far as I know, were introduced in a paper of Craig and Sulem in the early 90s. And one thing I would note about that is the paper of Craig and Sulem in the early 90s predated the well-posedness theory for order waves. So the point I want to make there is the structures that are necessary to keep the problem well posed were not yet understood at the time this numerical method was introduced, okay, by a little bit. I forget what year the Craig-Sulem paper was, maybe 93, and Sijew's paper was 97, and then other things came after that, okay? So the well-posedness theory was subtle, and the Craig-Sulem paper predated the robust well-posedness theory. Okay, in the truncated series model, the idea is that you can expand the operators x and y, which appeared on the previous slide, as a series in the elevation. So x and y depended on eta, the elevation of the free surface. So you can write out a series expansion for x and y for small deformations, and you can figure out explicitly some of the terms. X0 is just partial derivative with respect to x. Y0 is what we're calling lambda, which is the Hilbert transform with the x derivative, and so on. So you can keep going, figuring out additional terms. Okay, and so to form a truncated series model, you take the series that you figured out, you truncate the series after a fixed number of terms, after a finite number of terms, and then you substitute for x and y with these truncated versions. So x is the whole infinite series, y is a whole infinite series. Instead of using the whole series, you use just finitely many terms for each. Okay, that gets you your model. And I should point out, there are other ways to do that. So one other way to do that is to do an expansion for the Hamiltonian and truncate there and go from there. So there are choices to make in doing this. Right? This is not an argument from physical principles. This is throwing away terms. So there are a lot of ways to throw away terms. So, different versions of this might lead to slightly different truncated series models. Okay?
Excuse me, do you need this epsilon? That is, you don't need that.
I'm told in practice, what you get with the epsilon is the same as what you get without the epsilon. But the argument might be slightly more justified if you think of it in terms of the epsilon.
I use two terms now in my calculations, so similar. And it takes off. It's dramatic. It's something else than the small power. It takes the physics.
It what?
I mean, the leading few terms take the physics of the processes, usually.
Okay. All right. Okay.
It'll become more dramatic soon.
So the question, so here's the big question. The well-posedness theory for the full water wave took a long time to develop and turned out to be quite subtle. The truncated model, the truncation is not subtle at all. You just throw away a bunch of terms from the evolution equation. What are the chances that you are left with a well-posed problem from throwing away all these terms? Okay, so it's reasonable to ask, is the truncated series model itself a well-posed, does it have a well-posed initial value problem? And I think from the way I'm stating this and from the title of the talk, you can guess that the answer is no, you're not maintaining the structures necessary in the equation to be able to bound the growth of everything and get a well-posed problem. Okay, so that's where we're going. And so now let's look at the simplest truncated series model. Okay, so if you do your expansion for your operator x and your operator y, and you stop after just quadratic terms, you get this system. Eta t is lambda c minus dx, h eta lambda c. And so what this means, so again, I'll say lambda is the operator h dx, h is the Hilbert transform. This bracket is a commutator, so this means h of the product eta lambda c minus eta h of lambda c. So that commutator we apply a derivative to. And then ct is minus g eta, so that's the gravity term, plus 1/2 lambda c squared minus 1/2 cx squared. Okay, so this is what you get from truncating after just the quadratic terms. Okay, so you just keep a little bit from the series. Yes?
So just one question. So is that an infinite depth? Or?
I believe this is an infinite depth, yes.
Oh, you can have that in finite depths as well. The important point is x and y. But if you don't truncate these equations, the evolution equations, but you truncate only x and y and plug them in, so then they're very different.
I'm not sure I understand. So the operator capital X and the operator capital Y were truncated to form this equation.
I said two terms, quadratic, but you keep the whole, the exact, in particular the Bernoulli equation, the last, you keep that as exact as possible.
So
it's not consistent, but that is very different.
I'm not sure what you're saying. It sounds like you're saying to just use the Euler equations, right? That would be used to not approximate, to keep it as consistent as possible.
No, I think he's saying truncate the equation that you have a hard time with, that has the DNO in it. Don't truncate the other one.
Yeah.
Okay.
Because it's y which is difficult here.
It's capital Y which is difficult.
Yeah, the normal velocity.
So
If you
so Y
truncate
shows
that
up in
one,
both
keep the
equations.
rest. Evaluate everything. Then you have
Okay. Uh,
So I'll say one thing. So
Yeah.
the formulation's a little puzzling. What happened to G? And why are there X's and Y's? So I'll be honest. So G is the Dirichlet-Neumann operator, Dirichlet-Neumann data.
Yeah.
X and Y are a mix of the tangential and the normal.
Yes, yes.
So this is equivalent to water waves. That's not the way Walter wrote it, Walter and Catherine.
No,
The
no,
reason
okay,
we
okay.
wrote it this way is because a student of mine could not get her brain around the operator G, but she could get her brain around the operators X and Y. It's all the same. So what Walter and Catherine did is they had this set of evolution equations, but they had normal derivative and they had tangential.
Yeah.
So they did what you said. So what they did was a little dishonest. They only truncated the DNO, and they
Yes.
left all the tangential derivative terms.
That is
To arbitrary
that
order.
is the clever trick.
I'm not sure that their equations are any more well posed than these ones. But we were trying to be honest, and so we've tried to be consistent. That's right, that's right.
Okay.
In the way we truncated things.
Yeah, so in case it's not clear, I'll just say that in the collaboration, Dave is responsible for providing the equations. Yeah, I work on the equations Dave tells me to work on, you know. Yeah, so yeah, there are other ways to do things. This is the system I was told we were studying. Okay. Okay, so this is what you get in this way of doing the approximation, truncating after keeping just the quadratic terms. And I want to draw attention to this term here that I've boxed. Okay, so this says, if you ignore everything else, this says CT is like lambda c squared. Okay, if you didn't have the square there, if it were just CT equals lambda c, that's a parabolic equation. That would be a linear parabolic equation. Okay, and if you had CT equals lambda c, that's a backward parabolic equation. CT equals minus lambda c, that would be a forward parabolic equation. So this is a parabolic term, and I want to think of this as being a variable coefficient version of that equation that I just said. This is CT equals lambda c with the coefficient is equal to 1/2 lambda c. Okay, and lambda c necessarily has mean 0. It's a Hilbert transform and a derivative. Either one of those would make you have mean 0. So that means lambda c is sometimes positive, sometimes negative. So this is, to restate, if you had just this term, it's CT equals lambda c with a coefficient that's sometimes positive, sometimes negative. So it's a parabolic term of indefinite sign. This should cause growth. Okay, and this term is produced just by the truncation. Okay, this is not a term that is present in the physical problem. This is an effect of the truncation. Okay, so the question is, how bad is the growth caused by this term? And then after we understand how bad is the growth caused by this term, do all the other terms help balance that growth? Can you control it with the other terms? Okay, so the answer is going to be that we cannot control the growth, although we can't necessarily prove that. But we can prove things about the nature of the growth. Okay, so that's what we're going to start with. We're going to start just considering this term. And that's not quite true. We're going to consider the term next to it also, the cx squared. So we're going to consider what we call the reduced model, ct equals lambda c squared minus cx squared. I always say at this point, this is not meant to be a model for water waves at all. We're just understanding what kind of growth you can get from these terms. Okay,
So you already did a scaling to get rid of the 1/2? Or?
I just ignored the 1/2, but you know, I'm an analyst. Analysts don't always see the constants.
Or constant equivalent.
You define 1/2 to be 1.
But you can absorb it in time if you want.
It's a truncation
Time.
approximation.
That's right. You're done.
Sure.
You rescale time instead of volume.
So
Okay, but with some scaling.
yeah, so
Yeah.
I think the 1/2 doesn't
I don't
matter.
think the 1/2 matters.
So we just take this reduced model, the CX, so for the argument I'm going to show you, first we did it just with the lambda C squared, and then the reason to include the CX is because we can run the same argument and it doesn't hurt us. So it just gets us a little closer to the original system that we started with, okay? And so what I'm going to go through is a proof that this reduced model is ill-posed. And the ill-posedness, it is a backward parabolic equation. The ill-posedness is similar to the ill-posedness of the backward heat equation in that we're going to demonstrate a piece of initial data, a family of initial data, which are small amplitude fast oscillations, and for which we know that they generate growth. We can prove that if you start with an initial condition that's one of these small fast oscillations, we can prove that it grows arbitrarily fast. Okay? So we use a method that Jerry Bona taught me. It's a method of Bona and Weissler to prove that this reduced model is ill-posed. We write the Fourier series for Xi. So Xi is Ck of t e to the ikx. And we take Ck to be real, non-negative, and equal to Xi minus k. So these assumptions that Ck is real, non-negative, and equal to Xi minus k, it means that we're expanding Xi with a cosine series using non-negative coefficients. And the symmetries of the system are such that those properties will be maintained at positive times. Okay? So you can see that the positivity is made at positive times if we write the evolution equation for Ct, or the evolution equation for Ck. So we have lambda of Xi squared. The symbol of lambda is absolute k. The symbol of a partial derivative with respect to x, of course, is ik. And these are both quadratic, so we get a convolution in each term. And so then the evolution equation for Ck, you get absolute k minus ll plus k minus ll times Xi k minus l Cl. Okay? And so the absolute k minus ll, that's what you get from the lambda of Xi squared. The k minus ll, that's what you get from the Cx squared. And this will always be non-negative. You have the absolute value of something plus the thing. Okay, so that's non-negative. So that's why the positivity of the coefficients is maintained. So it's very convenient. Okay. So it's convenient because it's going to let us ignore whatever we want to ignore. Any coefficient is non-negative, so we can set up inequalities with the coefficients. Okay, so if we write out the evolution equations for the first few coefficients, this simplifies further because absolute k minus ll plus k minus ll will typically be 0. It'll only be non-zero for small values of l. Okay, so Xi1t is 0, Xi2t is 2 Xi1 squared, Xi3t is 8 Xi1 Xi2, and so on. Xi4t is 12 Xi1 Xi3 plus 8 Xi2 squared, and so on. So there are only so many coefficients that influence each one. And so what we're going to do is we're going to use this kind of tableau of coefficients to pick out a subsystem which we can demonstrate blows up. So we can set up a system of differential inequalities. Whatever term I want to focus on, I can focus on it. Let's say I picked out this Xi2 squared. The thing is that Xi4t is greater than or equal to 8 Xi2 squared. I can ignore this because the coefficients are non-negative. So I can pick out any coefficients I want on the right-hand sides and set up an inequality because I know all the coefficients are non-negative. Okay, so here's what we do. We fix a j in the natural numbers. We set Cj of 0 to be 1 over j and all other coefficients to be 0. Okay, so the initial data is going to be 1 over j cosine of jx. Okay, so with that family of initial data, let's see what we get. Well, we know Cjt is non-negative, so we throw away all the terms there. We get Cjt is non-negative, so it says that Cj of t is always at least 1 over j. Okay, then we go up in steps of j. We look at the 2j coefficient. And in the evolution equation, I can pick out any value of L I want, and I get Ckt is greater than or equal to the contribution from my favorite choice of L. Okay, okay, so I consider k equal to j, and I pick my favorite L, which is j. The evolution equation then gives me C2jt is greater than 2j squared cj squared. Okay, so the point is I already know about cj, it's at least 1 over j. So this tells me, I plug that in, this tells me that C2jt is at least 2, and so C2j is at least 2t when I integrate in time. Okay, I keep going like this. I go up in steps of j. So we started with j and then 2j. We prove this by induction. We go up to kmj. And by induction, our conclusion is that cmj is at least 1 over 2j 4jt to the m minus 1. Okay, so each time we use our previous step in the inequality, and then we integrate in time. Okay, and we get that. So that's great for our purpose. Our purpose is to show that this blows up. That is not an L2 by time t equal 1 over 4j. By t equals 1 over 4j, this piece of the inequality that depends on m has gone away. If t is 1 over 4j, this says cmj is at least 1 over 2j for any m. So it says you have infinitely many of the Fourier coefficients that are at least equal to 1 over 2j. So it means the coefficients no longer decay. Okay. So by t star equals 1 over 4j, the Fourier coefficients don't decay, and the solution is blown up. All right? So you start with 1 over j cosine of jx. You get blow up in, and so that's analytic. You get blow up in L2 or in whatever other space you want by time t star equals 1 over 4j. So that's ill-posedness. That's ill-posedness because it shows that smaller and smaller data blows up faster and faster. Okay, now the particular argument I just showed you is ill-posedness in the space hs for s less than 1. Right, because I said it's smaller and smaller data, but the question is small in what norm? The h1 norm of 1 over j cosine jx is uniformly equal to 1. Okay, so it's not small in h1, but it's small in hs for any s less than 1. And that's not the only version of this argument that we can do. I said you can, for whatever k you want to focus on, you can pick your favorite choices of L. Different choices and different initial conditions lead to ill-posedness arguments in different spaces. So the one that I just showed you is small in hs for s less than 1. We have versions of this with ill-posedness in hs for s less than 3. And you can certainly do it in any space you want. This is a backward parabolic equation. It's not going to get better by considering h4 instead of h3. It's not going to get better going further out. It's just when you prove it, you have to prove it using a particular choice of initial data and a particular choice of inequalities to focus on, and the ones that we've done go up to, say, h3. But I have no proof that it's ill-posed in every Sokolov space, but it should keep working as you make different choices. You can go higher and higher. Okay, so that is the reduced model. If we choose a small amplitude fast oscillation, we get blow up in the reduced model faster and faster. Okay, so the question is, do we observe the same behavior in the full truncated model? So we have to be careful what we call things. I don't want to say the full equation. That sounds like the Euler equations to me. So we settled on calling the kind of the toy system we just looked at the reduced model, and the model that we're really studying here, the full truncated model. Okay, and then we can be more specific if we say what order truncation we use. So we actually, I showed you what we call the model WW2, which is the full truncated model keeping quadratic terms. We also study the WW3 model, which is the full truncated model keeping cubic terms. Okay, so we want to take the initial data that we just looked at, things like 1 over j cosine of jx for c. We want to take that initial data and plug it into the WW2 and WW3 truncated series models and see if the additional terms that we neglected, if they mediate this growth. Okay? So the answer is they don't. So this is a table of data for WW2 and WW3. So as I said, those are truncated series models keeping quadratic and cubic terms. So I should say, when you go out to a further order, the old terms that you had are still there. So this parabolic term is there at every order. Cubic model just adds cubic terms on top of what was previously there. Okay, so the term that we studied will be there at any order. Okay, so this chart here is for the piece of data that I just showed you. So we take the initial surface to be 0 and the initial potential to be 1 over j cosine of jx. Okay, so I'll get to other families of data in a moment, but just for that family, we find these blow-up times. So here, this is the WW2 model, this is the WW3 model, and these are the results for j equals 2, 4, 8, and 16. And so you see it looks roughly, it looks very, very clearly here. As we double j, we get blow-up twice as fast. 0.3, 0.148, 0.073, 0.037. It looks like a clear factor of 2. Okay? So the blow-up time here, blow-up is in quotes. Blow-up should be in quotes on the following slides as well, I think. We define blow-up to be when the L infinity norm of the solution reached a prescribed level. So when it reached a prescribed threshold. So we didn't insist that the L infinity norm go out to infinity or machine infinity. If the L infinity, if your initial data was 1 over j cosine jx and the solution got to be, say, amplitude 10,000, that's when we stop the simulation. Okay, and this shows that shows ill-posedness. It shows that for smaller and smaller data, in this sense, in smaller in HS for s less than 1, for that smaller and smaller data, you got to, say, an L infinity norm of 10,000 faster and faster. So the growth rate goes faster as your data gets smaller. Okay, that's the hallmark of ill-posedness. Yeah.
Now your truncated model is Hamiltonian, who Dave just whispered this to me.
Okay.
The quadratic one. And so what happens to this conserved quantity? It must be indefinite or something.
We could go into the runs and see what happened, but it's not
If
something
it was
that,
definite, it could blow up. So
if it was
the
conserved,
original
then it was
Hamiltonian
definite.
is definite.
Okay. Yeah, so, yeah, we see growth, so,
Could you add terms to the truncation? Say that the WW2 model is indefinite. Could you add an extra term to make it definite again? That might help you. That's inconsistent, but at least it's consistent to quadratic order. That's an option if that would be the case. That WW2 is, sorry, WW2 is not definite.
So with different models, you could get different behavior, for sure. And if you start adding new terms, then you're outside the philosophy of the truncated series model philosophy, I think.
No, you can always add high order terms, but not consistently. That doesn't increase the order, but you might use them to get an extra property like definiteness if that's what you desire, right? And that's okay, I think. Isn't it, David?
You definitely want that.
I mean, for perturbation theory, that is okay, and since I saw an epsilon fly around, that is actually okay.
That's not the point, though, is the point is you're looking at this particular scheme and you want to know if these particular models
Sure.
are the
Yeah.
Sure.
Well, and the broader point is that one should be very careful when forming models of this kind. You can't just do anything and expect to have, say, a well-posed problem. So I keep saying this, but again, the original problem is quite subtle, and you can't just approximate it any way you want and keep key features like well-posedness.
So, one comment is the quadratic truncation has a cubic Hamiltonian, so that's by definition sign indefinite.
Yeah.
Yeah, I couldn't see that quickly, but sure.
What happened to the momentum? Is there a truncated momentum in this model?
I refer all questions on the model today.
That must be indefinite too. If it exists, the truncated momentum might not be a conserved quantity.
So let me ask a question. So this is actually the system that you integrated here.
That's right.
Not that little model which you proved.
That's right. This
that
is
use
This
the
is the WW2
Mark
model.
Rose's talk.
this
They use
is this
that
model
as
here.
proof of stability.
Right, eta and c. Right, not
It doesn't look- it
the
doesn't
little
look like
equation.
it's a combination.
Yeah. Okay, so yeah, so as Mark said, considering this model, which is a model that I believe is considered in the literature, you don't maintain well-posedness from the order wave system. Okay, we believe that these calculations are well resolved. They use a lot of spatial points, and one thing that I would say is that the WW3 model using the same data does blow up later. Okay, so it does seem there is some effect from including higher terms in the truncation. This is very crude here, but it's about 15% later for this family of data. Okay, and that'll be a trend as I keep showing a few additional numerical results. Okay, so for what we just saw so I'll go through a few more numerical results here. In what we just saw, the WW2 model with data 1 over j cosine jx for c, data 0 for eta, using j equals 16. This is what it looks like at what we call the blow-up time. Okay, so the spectrum. So this is the spectrum. It's clearly not decaying. It really has blown up. Okay, we probably could, by looking at the spectrum, have called the blow-up earlier, right? Like if this is the spectrum, it stopped decaying before we stopped the simulation. So some other measure of blow-up time would be even faster.
What's the piece up there?
Yeah, I mean, this is the spectrum. It's just what it looks like. So some wave numbers are higher, some wave numbers are smaller.
Oh, I see.
Yeah. Yeah, so those are the ones that have grown, I guess.
How big is them in the compilation?
What's that?
How big is the resolution?
I-
How big is it? Yeah, I see the K. There's beta K is one.
the Ks go, there's about 1,000 positive wave numbers, and the amplitude of them is higher than 10 to the 5.
Yeah.
Yeah.
So why are those zero, the higher ones?
Oh, so that's a
Oh, you have graphics.
that's a filtering scheme that we used.
As we did the simulation.
Right. So filtering is a good topic of discussion here. So people always filter these results, and a question is, how does the result that you get depend on the choice of filtering? So we filtered these at different levels, and this will come up on later slides. Let me just go there. So this is an example, again, of blow-up time versus P. P is a filtering parameter. So we either filter more or less, and we see if that has an impact. Okay, and the trend is always the same, that the top curve is j equal 4, the middle curve is j equals 8, the bottom curve is j equals 16. P is the filtering, so a vertical slice here shows them all at the same level of filtering. And kind of no matter what, you always see larger j blowing up faster. Okay, this is the WW2 model, and I said that these are for different values of j, but I didn't say yet how j enters in this family of data is eta is still initially 0, c initially is 1 over j to the 1/10 cosine x plus 2 over j to the 5/2 cosine jx. Okay, so the point is the 1 over j to the 10th cosine x, that goes to 0 with j. The 2 over j to the 5/2 cosine jx, that goes to 0 in in HS for s less than 2.5. Okay, so this is a significantly more regular family of data than the previous one. Okay, so this is going to 0 almost in H2.5.
Why did you need that first term at all?
To get the proof for the reduced model to work. So this uses the interaction between different modes. So the proof I demonstrated, you just worked in one ideal. You worked J, 2J, 3J, and 4J, and so on. So you can run the argument focusing on whatever choice of modes you want. So here, I ran the argument using J equals 1 and J, and getting an interaction. Yeah. But in a small way.
So, is it true that if you want to prove ill-posedness for HS less than S less than 1, you need interactions?
I mean, you can't really say that you can't prove
Yeah,
the
but I
theorem
mean-
without that. I mean, the way that I did it, I have one proof
Let me ask you
for
another way.
HS S less than 2, and that just works in a single ideal. That just goes J2, J3, J. That gets up to H2.
That
That
gets up
proof.
to H2, okay.
Yeah, so we did 3 families of data. We did the 1 over J cosine Jx. We did this family, 1 over J to the 1/10 cosine x plus 2 over J to the 5/2 cosine Jx. We also did 1 over J to the 3/2 cosine Jx, which fits into the first argument.
I see, okay.
And there's nothing special about 3/2. It's that we could
I
go
mean,
up
just
to
as a
2.
curiosity, if you had dropped that first term there,
Mhm. And just
would
do
you have
the
gotten
J to
blow
5/2.
in the times that you watched?
I'm not sure if we tried it or not. Yeah, we took the guidance from
No, I understand.
the proof.
I mean, obviously, there's still ill-posed, but it's might be hard to see ill-posedness.
Yeah, so to see the ill-posedness, you need just the right choice of data. If the ill-posedness is at all subtle, you need just the right choice of data. And this family is showing this for WW2. It's clear that the blow-up time is decreasing with J. So once again, as the data is getting smaller, the blow-up time is getting faster. And 1 over J to the 1/10 is not all that small. So, right, this is,
Yeah.
for J equals 16, that's 1 over 16 to the 1/10. This is not really a very small initial condition.
Is 1 as far as I'm concerned.
Okay, I wouldn't say it's quite 1. I think it might be close to a half.
Yeah.
Right. So this is not all that small, but this is blowing up pretty quickly. That's
Yeah.
0.06. And it's blowing up faster than much faster than when J was bigger. You
So
know,
these, in fact, are seeming to blow up even faster than the other,
uh,
than the previous ones, right?
well, let's see.
Oh,
So
no, 0.03, I think.
0.03 for 16. So a little slower, but still noticeably blowing up, and faster as the data gets smaller and smaller. Okay, so this is WW3 with the middle family that I said, 1 over J to the 3/2 cosine Jx. So in WW3, we still see the blow-up. The blow-up times are slower than they were for WW2, but you have the same trend regardless of the level of filtering. You have the same trend that the smaller data grows faster. Okay, and that's the clear ill-posedness. So here we have the cubic terms, and you have growth in the solution. So this is growth in the L infinity norm. And growth happens faster as the data gets smaller. Okay. And so then this is WW3 with the third family of data, the more regular family of data. The growth is not as dramatic. You have to go further out, and I think we adjusted the threshold for largeness from, say, 10,000 to maybe 10. So the L infinity norm getting to be 10 is this time. But the trend is still clear that the larger data is growing faster. Okay. So in every case that we ran for these 3 families of initial data, we always had the larger data growing faster. The larger data leading to faster growth. And so that's our ill-posedness. That's lack of continuity on the data. Okay, so let me make some comments on that. So what I just showed was not a proof of ill-posedness of WW2 or WW3. It was a proof of ill-posedness for this toy model, for this reduced model, and then numerical evidence that the full thing is ill-posed. Okay. When I gave this talk in Banff last year for the first time, Mike Siegel was in the audience, and Mike Siegel thought some about it afterwards, and then he and I talked later, and we believe we have a proof that the whole WW2 model is ill-posed. And so things to do then are to verify that we have a proof and to see if it extends to additional terms in the truncation like WW3. Okay? In practical terms, the addition of more terms slows the growth. So the growth was much slower in WW3 than in WW2, especially as the data got more regular. It's possible that in practice, using enough terms in the truncation might slow the growth enough that it's hard to see. So it's possible that, say for a fixed discretization, there's an appropriate level of truncation where the growth is so slow that you might not see it for your purposes. Also filtering, say on top of using enough terms for your level of discretization, filtering may help remove the ill-posedness so that in practice you might get decent results. But even if you don't necessarily always see the ill-posedness coming from this, one should be very careful using these methods, I would say. There is this underlying ill-posedness because the truncation is not respecting the structure of the equations. Okay, so generally speaking, I would say one should be very careful and try to ask if what they're seeing really reflects the order wave problem. Okay, so I guess I'll wrap up. I'll just say quickly, one thing you could do is where we actually started with this. So we started with this when Dave asked me how to prove something like the WW2 model with viscous terms is well posed. So there's a model by Diaz, Dyachenko, and Zakharov where you take the usual order wave equations and you put in some viscous terms. So you put in some linear viscous terms. So this is not how you would actually have a viscous water wave. A real viscous water wave would use, say, the Navier-Stokes equations with a free surface, which people do study. But this is intended as a physically motivated model of viscous water waves. Okay, so that's the Diaz-Dyachenko-Zakharov equation. It has this 2 new Laplacian x eta and 2 new dy squared phi in there. Maybe there's a term missing also, I'm not sure. But that's the DDZ model. And then if you apply the truncated series philosophy to this model, you get what we got before, but now with viscous contributions. Okay, so now you get 2 new dx squared eta, 2 new dx squared c. You get some other terms with eta in them, but you have these viscous terms. Okay, with the addition of the viscous terms, you get a well-posed initial value problem. So the viscous terms give you control over higher norm. That higher norm controls the problematic term. Okay, so the proof is by the energy method. I think I'll skip this. I'll certainly talk more about the energy method in the summer school next week. So I'll just want to talk about the steps of the energy method here. But the point is, there's a bad term that you need to estimate. You can estimate it in terms of s+1 derivatives of xi, and the viscosity gives you control exactly over terms like that. Okay, so with the viscosity, you get a well-posed problem. Okay, and including the viscosity could be viewed as a kind of regularization you can do of the equation. Then you would need to balance your viscosity parameter versus your truncation level to try to make sure the viscosity isn't destroying your structures, but you're still getting a well-posed problem as long as you have the viscosity there. Okay. Okay, so something Paul and Jan Wang and I have been talking about then is, does surface tension remove the ill-posedness? So Jan has run a couple simulations in the past few days. I think it's fair to say that the early indication is that he's not getting evidence of the ill-posedness from the same family of initial data that we had. I would say that it's far too early to draw a conclusion. My belief is that the surface tension does not remove the ill-posedness. The regularizing effect of surface tension has been proved. It's been proved to be 1/4 derivative. So you gain 1/4 derivative over the initial data in a time average sense from the Kato smoothing effect from surface tension. So there are two proofs of that. One is by Alizard, Berkenzuli. The other is by Vera Herr and Staffelani and Christensen. Okay, so the result is you gain a quarter derivative in a time average sense. The quarter derivative does not strike me as strong enough to remove the effect of this parabolic term.
What does viscosity give you?
Viscosity gives you one whole derivative.
So if you took higher order viscosity, would it,
That would be fine.
if you took a fourth order derivative rather than a second, say for example?
Yeah, that would be fine. That would give you control over two derivatives, which is just way more than you need. Yeah, the second order viscosity is enough.
Since you've mentioned that, so Zan has run these things for last couple of days only,
Right.
and the same initial data doesn't blow up to time 100.
Mm-hmm.
With truncated model.
With WW3 model.
With surface tension.
With surface tension. And if you look at, different families, it doesn't seem like the H1 norm does anything over times of order 100.
Mm-hmm.
What do you do with the surface tension term? You keep the whole thing, or you truncate that after
We've,
cubic?
we've done both, just keeping linear surface tension term and putting the whole thing in.
I wonder if that's an effect on the Hamiltonian, because you get an extra term in your Hamiltonian with the surface tension.
Mm-hmm.
So that might be actually adding some definiteness to the Hamiltonian, if possible.
Yeah.
Surface tension coefficient is probably small, so.
So the main thing I would say about this is it's too early to be definite,
Yeah.
but we're looking into it.
So essentially really matters for very short waves only. For the long waves, they
Sure.
rather short.
Sure.
So of course, well, it's the strongest blower for the shortest waves.
So the data that we're using has high wave number. So those are fast oscillations, right? So they would be short waves.
I've been doing very simplified quadratic calculations now for internal waves, and of course the reason why this works so well. First, the quadratic is rapid and feasible on small computers because it's few. But the reason is that the waves are long.
Mm-hmm.
You don't trigger the. It's possible to drive the excitation, so you trigger it, but then.
Yeah. So
this
this
is a
is
very interesting range where you have like.
This is worsted highest wave
100K,
numbers.
and it's no difference between cubic and quadratic. But when you come into short wave regime, then of course that's a different story. And if you let time go on, of course it diverges.
Mm-hmm.
But I mean, the many interesting processes are for. I mean, you can study very many interesting processes in a local time frame.
But the point is,
rapid, so that's a different point, of course. Yes.
yeah, but the point is, without surface tension, the problem being ill-posed doesn't. I mean, the
Yeah, so
statement
we're
is a
talking
statement about the problem,
Yeah, so
right?
it's
So
a-
long waves, short waves, it doesn't matter. There's something wrong with the equation,
Yeah,
right?
And the data that we're using to bring that out is with high wave numbers.
That's
So
right.
short waves.
Yeah.
But yeah, but generally the initial value problem is a bad problem.
Well, it's like the backward heat equation. I mean, you
It
can
is like
solve
the
it for
backward heat
long
equation.
times if you just try cosine of x. Right? It's okay.
That's true. Right. Okay, so just finishing up. So my intuition, the way I think about this, the gain of a quarter derivative from surface tension should not be enough to balance this. If the growth is arrested by surface tension, I would really like to understand the mechanism. Because I don't see how to make the estimates just by adding surface tension. Higher order dispersive smoothing, like from an elastic wave, e.g. Toland's hydroelastic waves, would be 3/4 of a derivative. I think that could be enough. And so for hydroelastic waves, you might not have the same problem. Okay, that's all kind of a viewpoint and not a proof, but that's where we are. All right, thanks.
There were already many questions, so maybe some Because of questions or comments?
I have a quick question.
Mhm.
So, actually, either one of you, so you were talking about the numerics, and you mentioned WW3, did you also test WW2 with surface tension?
WW2, in my view, is a sort of flawed model to start off with, because of non-sign definiteness of the Hamiltonian,
And that's still.
and
the same
because it
concept?
also in gravity waves doesn't have quartets, which is the only thing there are in gravity waves. So there's lots of good reasons. If you're doing surface gravity waves, not long internal waves, for example, that's a different matter. Doing surface gravity waves in deep water, WW2 doesn't make any sense.
And I guess with that expansion order, the Hamiltonian with surface tension still remains sign indefinite? Is that the case?
I'm sorry, with surface tension? Yes, because it's the part that has to do with the potential flow that's assigned indefinite.
Is WW3 sign definite without surface tension?
We would guess not, it's blowing up.
Oh, yeah.
I mean, I don't know, right? I mean, it has to do
Someone must have
with.
written it down.
I still don't understand why you cannot make it sign definite by slightly altering your truncation order. But I don't understand that.
So there are also various forms of WW2, WW3, right? So one form is you truncate in the Hamiltonian, and then you take the variational principle. And another form is you vary and then truncate. And those are not the same.
I understand, but to get sign definiteness, you have to, the cubic kinetic term, you have to truncate it a certain way to keep it sign definite. But then, and that will mix up the orders. That's what that has to do. You already see that. So I'm slightly puzzled why that's not possible.
Yeah, well, I don't know if it's not possible. I don't know.
I mean,
I don't know if it's even sign definite, so I don't.
I mean, you could form many models, and for these models, this is what we found.
Here I thought your punchline was gonna be, oh, by the way, if you tweak it this way, it works perfectly.
Oh, so that
Takes a
isn't-
full problem, yeah.
that is an area of current research. So I believe there is a way to change it, but we haven't worked that out yet. Right, so well, what I just said was too strong. There may be a way to do the truncation while respecting the structure that led to the well-posedness and leading to a
That is to
well-posed
say,
problem. But
it's
we're
an
not there
incredible
yet.
way to, and also that there's.
so maybe next time I'll
Okay,
talk about,
yeah,
you know, if you see me talk about this in a year or two, maybe that'll be the punchline.
Yeah, well, maybe you'll be able to.
Yes, I plan to be.
Okay, yeah.
There will be some kind of truncations you can do which will lead to well-thought models, presumably. You're definitely not saying that whatever you do is going to be bad.
I'm especially saying you need to be careful. Yeah, yeah.
Okay, so on this, maybe thanks again, and we move to the next talk when we get to see.